In this module, you will learn the basic skills needed to use Code Composer Studio. Also, you will learn about a linker command file and understand why and how it is used. Code Composer Studio is an integrated development environment that integrates the edit, code generation, and debug process. It is simple to use with single-click access to various functions and provides powerful debugging tools. Scripts automate tasks and BIOS is built in. Code Composer Studio is based on the Eclipse open source software framework. Code Composer Studio has edit and debug perspectives. Each perspective provides a set of functionality aimed at accomplishing a specific task. In the edit perspective, views used during code development are displayed, and in the debug perspective, views used during debug are displayed. A project contains files such as C and assembly source files, libraries, BIOS configuration files, and linker command files. It also contains settings such as build options, which include the compiler, assembler, linker, and BIOS, as well as build configurations. To create a project in Code Composer Studio, you would click on File, New, CCS Project. First, you'd fill out the project name, the location, and the device, then take care of the advanced settings, and finally, the project template. You will have a chance to try this in our first lab exercise. After a project is created, the build options are configured. In our lab exercise, we will look at the options for the compiler and linker. All code consists of different parts called sections. All default section names begin with a dot and are typically lowercase. The compiler has default section names for initialized and uninitialized sections. For example, X and Y are global variables and they are placed in the section .ebss, whereas 2 and 7 are initialized values and they are placed in a section called .cinit. The local variables are in a section .stack and the code is placed in a section called .text. This is a small list of compiler default section names. The top group are initialized sections and they are linked to Flash. In our previous code example, we saw .text was used for code and .cinit for initialized values. The bottom group are uninitialized sections and they are linked to RAM. Once again, in our previous example, we saw .ebss used for global variables and .stack for local variables. Next, we need to place the sections that were created by the compiler into the appropriate memory space. The uninitialized sections .ebss and .stack need to be placed into RAM, while the initialized sections .cinit and .text need to be placed into Flash. The linker command file describes the physical hardware memory and specifies where the sections are placed in the memory. The file created during the link process is a .out file. This is the file that will be loaded into the microcontroller. As an option, we can generate a map file which will tell us the absolute address and size of each section. A linker command file consists of two sections, a memory section and a section section. In the memory section, page 0 defines the program memory space and page 1 defines the data memory space. Each memory block is given a unique name along with its origin and length. In the section section, the section is directed to the appropriate memory block. In the lab exercise, you will have an opportunity to work with a linker command file. In this lab exercise, you will work with a linker command file and learn the basic skills for using Code Composer Studio. You will set up a target configuration, create a project, build a project, and step through the code. You can pause this presentation now and try this lab exercise on your own, or you can watch me do the lab exercise. At this point, the control stick is plugged into a USB port on the computer. Code Composer Studio has been started, and we are using the default location for the workspace folder. The first time CCS opens, a Welcome to Code Composer Studio V5 page appears. I will close this page by clicking the X on the TI Resource Explorer tab. We now have an empty workbench, which refers to the desktop development environment. The workbench opens in the CCS Edit Perspective view. Notice the CCS Edit icon in the upper right-hand corner. A CCS Debug Perspective view will automatically be enabled when the debug session is started. First, let's set up the target configuration by clicking File, New, Target Configuration. We will name the file F28069 underscore CTRLSTK.ccxml. This is just a descriptive name since multiple target configuration files can be created. We will leave the Use Shared Location box checked and select Finish. We will set the connection type to Texas Instruments XDS100V1 USB emulator. And then we will filter our options to F28069 and select Control Stick Piccolo F28069 by placing a check in the box, and we will save the configuration file by clicking Save, and we will close the setup by clicking the X on the tab. In the future, you can view the target configurations by clicking View, Target Configurations, and under the User Defined folder, you will find the configuration we just created. If we had multiple configuration files, we would simply right-click and set the appropriate one as the default. Currently, we only have one, and it is set as default. I will now close out the target configuration view window. The next step is to create a new project, and we will create a new project by clicking File, New, CCS Project, and we will give it a project name of Lab 1. And we will uncheck the Use Default Location and navigate to our lab files, which are located on the C drive in the 28X folder under Labs, Lab 1, and we will create the project in the Lab 1 project folder. Next, we will select the device family as C2000. We will filter our options to the 2806X Piccolo, and we will select the Control Stick Piccolo F28069. We will leave the connection blank since we've already set up the target configuration file. Under Advanced Settings, we will change the link command file to None. We will be using our own link command file rather than the one supplied by CCS, and we will leave the runtime support library set as automatic, and CCS will automatically select the appropriate runtime support library for our device. Under the project templates, we will select Empty Project. The very top Empty Project will be selected. If we do not select the one below will create an empty main.c file in the project, which is not needed for this lab exercise. So please be sure to select the top one, Empty Project, and then click Finish. You will notice that the Lab 1 project is now listed in the Project Explorer window, and the next step is to add source files to the project. We will right-click on the project and select Add Files, and then navigate back to our lab folder, C28X, Labs, Lab 1, and the files will be located in the Files folder. And if you notice, we have two files listed. We will select both of the files and click Open, and we will copy the files to our project, and you will notice that the files have been added to our project. Next, we'll take a look at the project build options, and by right-clicking on the project and selecting Properties, you will notice that the build options for the compiler and linker are listed. Looking at the linker build options, we are specifying an output file name as well as a map file, and what we'll do is we'll change the stack size to 200. And then in the compiler processor options, you'll notice that we have used large memory model and unified memory both checked, as well as specifying support for CLA, floating point, and VCU, which are available on our device. Most of the default options that we have that are selected are more than sufficient for this lab exercise, and we will click OK to save the build options. Now we'll take a look at the linker command file, and you will notice that the linker command file has been configured as described in the objective section on the slide in the lab exercise manual. You will notice that L3 DP SARAM and L4 SARAM are located on page 0 for program memory. The remaining memory blocks are located on page 1 in the data memory space, and the sections have been linked to their appropriate memory blocks. There are two buttons on the horizontal toolbar that control code generation. The first one here is the build button, which will do a full build and link of all source files. And we have the debug button, which will automatically build, link, load, and launch a debug session. Okay, first what we'll do is we'll click the build button, and we will watch the tools run in the console window and check for errors in the problem window. We've deliberately put an error in the lab file so you can see what would happen when you encounter an error, and we will take a look at that error now. And by simply double clicking on the error, it will open up the file with the error, and at the question mark line we have the error. We can see we're missing a semicolon. For future knowledge, realize that a single code error can sometimes generate multiple error messages at build time. This was not the case here. So we will build the project again, and there should be no errors this time. Okay, next what we'll do is we're going to click the debug button, and the debug button, as I mentioned earlier, will save modified source files, build the project, open the debug perspective view, connect and download it to the target, and then run the program to the beginning of the main function. So let's click that now. And as you can see in the right hand corner of the screen, we are now in the CCS debug view. And we are loading it to the target, and we are now connected to the target. So what has happened at this point is the program ran through the C environment initialization routine in the runtime support library and stopped at main in lab1.c. So now we're in the debug perspective, as you can see from the upper corner right here, and it's standard practice to while debugging to watch local and global variables. So let's take a look at these right now. What we'll do is we'll open a memory browser by clicking View, Memory Browser, and we'll browse the global variable Z right over here. And what we do is we type an ampersand, meaning the address of. So when using symbols in a memory browser, you need to use an ampersand if you're using a symbol. So we'll use ampersand Z, and we know it's in a data space, and we're going to select Go, and now we have that listed here in the memory browser. Also notice that in the variables window, it automatically opened, and the local variables X and Y are present. The variables window will always contain the local variables for the code function being currently executed. Next what we'll do is we'll add a global variable to the expression window. So we'll open the expression window, and we'll add the global variable Z just by typing Z and enter. And if you notice, we did not use an ampersand sign here. The expression window knows that we are specifying a symbol. I can change the value in the expression window. For example, I will change this to 5, and you'll notice that it will change to 5 in the memory browser window as well, which it did. And I can go into the memory browser window and change it to some other value, and it will change back in the expression window. So next step, let's take a look at the local variables, and what we'll do is we'll single step the code using the step into button or F5 on the keyboard. And you will see that when I execute this next line of code in the variables window, X will change to 2, which it does. And now when I execute the next line, Y will become 7, and it does. And then finally, when we execute the next line, 2 plus 7, we should get 9 at the Z location, which we do. Okay, so that works. And right now, what we're going to do next is terminate the debug session by clicking this button here. And that brings us back out to the CCS edit perspective. And then we will close the project by right-clicking on the project and selecting Close Project.